Cantor's diagonalization, baby. This is one of the most famous proofs ever, and it can be applied to a crap ton of stuff. I included some other videos. The key takeaway of the first one for people struggling to understand diagonalization is if you have your chart here and you write out every number. So if you say like these are the integers and these are the positions of each integer, so it just goes one integer, another one, another one, another one, another one, and you take any given position along that integer, like it shows over here, and you add the if you take the diagonal and add 1 to it, in the case of integers, like integer strings, then you're going to end up with a number where the first number of this one doesn't match, the first number of the second number of this one doesn't match, the third number of this one doesn't match, fourth number of this one doesn't match, fifth over here doesn't match, and that will go on infinitely. So every single position is one off from every other infinitely listed, infinitely counted, infinitely enumerated number that's on the list. So you can take that number and be like, oh, we found a new one, add that to the list, and then you just have another tail on your infinite set there that you're like, well, let's just flip this last one. And if this number we added to the list wasn't on there, then flipping the last bit will also not be on there, and flipping the last bit will also not be on there, and then flipping the last bit will also not be on there, and you can do that infinitely. So in the case of binary numbers, these binary strings, which is the set beta, if you take all of these and you flip them, which is counter D, the second video that I recommended calls it counter D, but in this case, right, if you add 1 like you would with integers, then it's no longer in the set beta. So what this proof does is if you do 1 minus whatever that bit at that index is, then you're going to end up with either 1 minus 0 or 1 minus 1, and you're going to end up flipping that. So if it was 0, it is now a 1. If it was 1, it's now 0. So this little bit of math here is just flip the bit at any given index of any given b, any given b in the set of beta, and you're going to end up with another binary string. So that's the core of this proof, and there's some preamble there where we're talking about the set of integers and versus binary. So we already talked about that. Sorry, I am sick, so this is very hard to not be snorting and coughing. So we've gone through and we've showed you can always add to the already enumerated set of binary strings. So when we're talking about the actual contradiction is let beta be the set of all infinite sequences over 0 and 1, which is all the binary strings, show that beta is uncountable using a proof by diagonalization. So we said that with a lot of words, but a more elegant and concise mathematical way to express that is by constructing D, an infinite sequence where every D sub n is either 0 or 1. So D is an infinite sequence over 0 and 1, which is the definition of beta. Therefore, D is an element of beta. So we came up with a binary string. That's all that's saying. So, and since it is a binary string, it is in the set of binary strings. Words. So we're going to prove that D is not in the list of B1, B2, B3, which is the enumeration table of all binary strings. So suppose towards contradiction that D equals B of n, meaning it matches one of the previously enumerated binary strings. So we're going to assume that's true. We're going to assume that it's already been counted and there are no other strings that can be added to this binary set. Then they agree at every position, including n. So, which is just saying that if B of 3 equals D, then they're going to agree at every single position. Then they must agree at every position. So D sub n equals B sub n. But by constructing D sub n equals the inversion, so this is counter D if you're looking at video number 2, then it does not equal the B sub n, because there's at least one bit that has been flipped. And the by the way, D is for the diagonal. So there's at least one bit that does not match the B sub n of any enumerated binary string, which is what I was showing. So if this matches, right, if we set the diagonal equals B sub 2, and we take this diagonal and we flip each bit, then this bit is not going to match. So position 2 of B sub 2. So, and this is position n of B sub n, which is just saying that bit is always going to be different and you're going to have to enumerate that, and it goes on infinitely. So the diagonal does not equal B at position n for every n. In the sequence, the diagonal sequence doesn't appear anywhere in the list. So putting it together, we assume that the set of all binaries contains a countable list of binary enumerations. We then exhibited a specific element, the diagonal. We proved that that is in the set of beta that is missing from the enumerated list. That is a contradiction, so our assumption was wrong. Therefore, no countable list can exhaust the string of all, or the set of all binary strings. So why this matters, right? In order for a Turing machine to be a usable alphabet, it has to be countably infinite. And then this goes into that. So the set of all Turing machines is countable, meaning every alphabet that a machine uses has to be defined. So if it's uncountable, you can't define it. Because each Turing machine has a finite description that can be encoded as the finite string, then there are only countably many infinite strings over a finite alphabet. So each language L over the alphabets of 0 and 1 can be represented by the characteristic sequence. The infinite binary sequence, whose ith bit is 1 if the ith string, the length lex order, is in L, so the language, and 0 otherwise. So this is the bijection between languages over 0 and 1, and that is the set of all binary strings. So the set of all language corresponds to beta, which we just proved is uncountable. So countably many recognizers versus uncountably many languages. Therefore, most languages have no recognizer at all. And to make this more succinct, there is an infinite number of languages that a recognizer will not recognize. Yeah, that has no recognizer. So if we have any countably infinite alphabet to recognize that language, there's an infinite number of languages that each one of those does not recognize, which is the more or less the same relationship between integers and real numbers, right? Because there's an infinite number of other numbers in between each integer. So there's an infinite number of infinities. So, yeah. Yeah, here's some more videos. I love Vsauce number file. The ones that I added in the document or the post thing reply response, I think the first one sets up a very like elementary school version of like what is diagonalization and how do we talk about integers versus real numbers, and then the second video assumes you know everything from the first video and how diagonalization works, and it specifically calls out another very important proof, which is the halting problem, and why there is no program that can determine whether or not another program halts, and it uses the same diagonalization. I hope that makes sense.